Hello everyone, here is Xu Jiazhu, PhD student under the supervision of Professor Surrogate at the Chair of Risk, Safety, and Uncertainty Quantification in ETH Zurich. In this video, I would like to share my research with you, which is surrogating the response probability density function of stochastic simulators using generalized lambda distributions. In this presentation, I will first of all give a brief introduction about what stochastic simulators are and why we need to surrogate them. Then I will focus on the generalized lambda model that we proposed to emulate stochastic simulators. I will illustrate the performance of the developed methods through a numerical example. Finally, I will end up with the conclusions and outlook for future research. A simulator is a computational model that is created to mimic the real world. For example, if we want to know the mechanical behavior of an aircraft under some extreme climate condition, we can create a finite element model to analyze its resistance to environmental loads. In general, there are two classes of simulators. The first one is the so-called deterministic simulator. Deterministic in the sense that when fixing the input parameters, repeated runs of the simulator provide exactly the same output quantity of interest. In contrast, stochastic simulators return different results when run twice with the same input parameters. In other words, the output of a stochastic simulator is a random variable. The random nature sounds a bit weird. Where does the randomness come from? On the one hand, a stochastic simulator can be considered as a deterministic function, but we cannot fully access all the input parameters. When fixing a part of the input parameters, x, and let the others z vary in their range of definition, the output becomes random. On the other hand, we can control all the relevant variables, x and z, but the input dimension is too high to work with. As a result, we control only a few of them and consider the others as noisy variables. To illustrate these two kinds of randomness, let's look at an example from the wind turbine design. A typical wind turbine simulation consists of two parts: the wind generation and the aeroservoelastic simulation, which takes the generated wind field as input and computes the structural response as output. In the generation phase, the simulator takes some macroscopic values as input, such as the mean speed, turbulence intensity, and so on and so forth. However, these synthetic values cannot uniquely define a wind field. Therefore, the generator uses random seeds on top of the well-defined characteristic variables to have a coherent inflow. Considering both simulations as one simulator, fixing these macroscopic values, the structural response is uncertain. If we only look at the second part, the aeroservoelastic simulator is deterministic. However, the input is a time series that can have thousands of dimensions. To study the property of the mechanical behavior of the turbine, we extract some synthetic values from the time series, which finally corresponds to the second kind of randomness. As are well known, high-fidelity simulators can be very costly. Due to the random nature, stochastic simulators should be repeatedly run many times with the same input parameters to fully characterize the output. Moreover, in the context of robust design, we want to choose the best parameters x to optimize certain functions. Suppose that we are designing the wings of an aircraft. When we fix the shape of the wings, due to the environmental uncertainty, the lift force is uncertain. The objective is then to find the best shape that maximizes the lift force in expectation. To this end, we need to explore the design space and carry out replications for each point in the design space. Consequently, many model evaluations are necessary, which requires a high computational power. In order to alleviate the burden, we propose using a surrogate model which mimics the original computational model. We want the surrogate model to be non-intrusive so that we can treat the simulator as a black box without entering into the complex code. The surrogate model should, of course, be accurate for the quantity of interest estimation. Last but not least, The surrogate model should be easy to evaluate. Otherwise, if it is as costly as the original physical model, there's no benefit to use such a surrogate. In this study, we are interested in surrogating the response probability density function of stochastic simulators. To fulfill these requirements, we propose the so-called generalized lambda model. This model is under the assumption that the response distribution can be approximated by the generalized lambda distribution. The generalized lambda distribution is a highly flexible distribution family that is able to approximate many parametric distributions, such as normal, students t, exponential, Weibull, gamma, beta, and so on and so forth. Instead of directly parametrizing the density function, the generalized lambda distribution parametrizes the quantile function with 4 parameters, lambda 1 to lambda 4. From the quantile function, we can compute the density function. However, the density function does not have an explicit form because we need to solve a nonlinear equation. For parametric estimations, many methods have been proposed, such as the method of moments, maximum likelihood estimation, maximum spacing estimation, etc. In this study, we applied the maximum likelihood estimation. Under the assumption mentioned before, for each given x, the output follows a generalized lambda distribution. When changing the input x, the distribution parameters will also change. As a result, lambda 1 to lambda 4 are actually deterministic functions of the input variables. We proposed using polynomial calculus expansions to represent these 4 functions. The function psi are multivariate basis functions. They are defined as the product of univariant Cow basis functions which are constructed mutually orthogonal with respect to the marginal distribution of each component of the input parameters. A are the model parameters to be estimated from the data. One intuitive way to construct a stochastic surrogate model is the two-step algorithm. As the name indicates, this algorithm consists of 2 steps. The first step estimates the distribution parameters based on repeated model evaluations with the same input. Here, xi is the i's point of experimental design, and yir is the output of the r's replication associated to xi. Because we cannot access the true value of lambda xi, the estimated value is equal to the true value disturbed by some noise. The second step then uses the estimated value to build a surrogate for each lambda. To illustrate this procedure, let's consider a stochastic simulator with one-dimensional input. As we can observe, for the same x, the simulator produces different results. At the first step, we locally estimate the distribution parameters based on replicates. Here, we have the local estimate for each lambda. As mentioned before, the estimated values are not exactly located on the reference, but scattered around the true value. Then, we build sparse polynomial calculus expansions for each distribution parameters, which are expected to reveal the underlying model. As you may remark from the illustration, the local inference can be very noisy, especially in the case of a few replications. These figures show the result with only 20 replications. The local estimates are far from the reference, especially lambda 2, lambda 3, and lambda 4. The inaccurate local inference results in a very poor performance of the surrogate in the second step. Consequently, to have a very good surrogate quality, the two-step algorithm requires a lot of replications. The problem actually comes from the fact that the two-step algorithm solves 2 separate optimization problems. The first one only takes the replicates into account for local inference, and the second optimization problem only uses the result of the first step and the points of the experimental design. Consequently, all the available data are never used in the same place. Now the question is, how can we use all of the data to improve the surrogate quality. Inspired by the generalized linear model, we propose the joint modeling framework. In this new algorithm, we first apply the two-step algorithm to have a preliminary estimate of the model parameters and select a set of basis functions for each lambda. We then apply an additional optimization step to recalculate the parameters associated to the selected basis functions, where we will use all the data at once. From a theoretical perspective, this additional optimization problem is equivalent to maximizing the likelihood of the joint distribution of x and y. The joint distribution can be decomposed as the conditional one that we want to estimate and the marginal distribution of x. Because we do not have parameters in the marginal distribution, the maximum likelihood estimator of the joint distribution ends up with the form shown here. To evaluate the likelihood of x and y with given model parameters a, we first evaluate the basis functions at x, and then multiply them with the model parameters to calculate locally the associated distribution parameters. As mentioned before, the density function is not explicitly given. We need to solve nonlinear equations to numerically evaluate the likelihood. Solving this additional optimization problem, we get much better results. The green lines here are the results of the new method, which is much closer to the reference. Now let's look at the performance of the two proposed algorithms through an analytical example. The stochastic simulator is defined as a deterministic function of x and z, but we do not control the value of z and let them vary freely according to their underlying distribution. In this case study, z are multivariate Gaussian random variables of dimension 5. The input parameters lie in a 5-dimensional unit hypercube. The output for a given input vector follows also a normal distribution with the mean and standard deviation as a function of x, as we can observe from the figure. The two figures show the probability density function of yx at two different points, with the training data consisting of 50 points of the experimental design and 25 replications. Clearly, the two-step algorithm cannot really capture the shape of the distribution. Well, the joint model can much better approximate the reference. To have more quantitative results, we investigate convergence analysis of the two algorithms. The error measure we used here is the Hellinger distance averaged over 1000 test points between the true distribution and the generalized lambda approximation built with the two algorithms. When a few replications are available, the two-step algorithm shows a very poor convergence rate. As expected, the joint modeling framework provides much more accurate results. With only 25 points of the experimental design, the joint model gives better results than the two-step algorithm with even 200 points of the experimental design. If we increase the number of replications, the two-step algorithm is improved. Well, the joint model still outperforms it. To conclude, the development of surrogate models for stochastic simulators are still in its infancy. We propose using generalized lambda distributions to approximate the response distributions. Two algorithms are developed to build the generalized lambda model based on polynomial Kells expansions. The first one is the two-step algorithm, and the second one, the joint modeling framework, which solves one additional optimization problem. We have tested both methods through various analytical examples, and the joint modeling framework always outperforms the two-step algorithm. We are validating both algorithms on real dataset. For example, the wind turbine case study that I talked about at the beginning of this presentation. Besides, from a theoretical perspective, the joint modeling framework does not require replications. As a result, we are elaborating this idea to propose new methods that do not need replications to further reduce the total number of necessary model runs. Thank you very much for your attention. I hope you enjoyed this video. I look forward to meeting you in Seoul.